right, I'll introduce our first and only speaker for this particular session. You are special.
Oh.
Nick Camacho, and he's going to talk about holomorphic differentials of projective curves.
Yes. Thank you so much, Beth. Thank you for USTARS for having me. This is my 4th year at USTARS, and I love it every year. So thank you again. And thank you all for coming to my talk. So, as Beth said, and as my slide says, we're going to talk about holomorphic differentials of projective curves. So yes, I will define what all those words mean, and we're going to have a lot of fun. So the first half of my talk is really just explaining a lot of the terms, and I'm hoping that everyone can learn something and get something out of it, and then the last half will be more of a result and getting down to a little bit more advanced things, if you will. So let's get started. So first, let's discuss what we're going to be discussing. So I'm going to first define a representation, give an example of what it is and how to think about them. Then we're going to switch over to some geometry, talk about projective curves, what's the definition, and what are the relevant properties for my talk that we need to keep in mind. Then we're going to talk about this module of relative differentials, and we're going to talk about a sheaf of relative differentials, and spoiler, this sheaf will have stocks that are these modules of differentials. So finally, we're going to talk about holomorphic differentials and define what that is in terms of the sheaf. And then in this last section, we'll discuss the representation theory of holomorphic differentials. Okay, representations. Let's get moving. So what is it? What is representation? So to define a representation, we need to consider 3 algebraic structures. We need a field, K, a fixed field, K, a vector space, V, of course, over K, and we need a finite group. Now, you can think about vector spaces being infinite dimensional or finite dimensional in general with representation theory, but we're going to think about finite dimensional vector spaces, and similarly for the group G, it's going to be a finite group G. So everything's finite, so we don't get too crazy with infinite dimensional vector spaces and infinitely sized groups. So what is it? You have these 3 structures. A representation of G is a vector space together with a linear action of G on the vector space. And so, in other words, we can think of a representation as assigning every element of G a linear map, a linear transformation, a matrix that acts on this vector space. And together with those 2 things, that's enough. So if you have a vector space, an action by matrices of the group on the vector space, that is a representation of G in V over the field K. All right, so I'll stop here. Any questions on what a representation is? We're going to go to an example here. But okay, cool. Okay, so let's look at this example. So we're going to let our field be R, our vector space be R2, and our group be some finite cyclic group generated by little g. And to give a representation, I need to tell you how every element of G acts on R2. Well, since it's a cyclic group, it's enough to tell you what the generator does. And so I'm going to say the generator acts on R2 by this matrix 0, -1, 1, 0. And what that means is G, the generator, is going to act by rotation counterclockwise on every vector by pi over 2 radians, 90 degrees. So more generally, we could have G, the generator, little g act, as this matrix, which is, does anyone know what this does? What does this matrix do? Yeah, it rotates by theta, counterclockwise about the origin, right? So you plug in pi over 2 and you get the top example. So that's all we have. We have a vector space and a group that knows how to act on the vector space by matrices. Okay. So, some questions in representation theory. What do we want to know? Well, if we fix a field K and we fix the group G, what are 2 of the big questions? Well, one of them is, what are the irreducible representations of the group over the field? And so if I fix a field K and then vary the group, that will give me all different kinds of irreducible representations. So, different irreducible representations. So the analogy that I want to use is atoms. So in our universe, there are finitely many atoms that make up every molecule, every substance. And so the atoms are building blocks of molecules, building blocks of everything, and so in the universe of a fixed field K and a fixed finite group G, the irreducible representations are the building blocks for all representations. And so carbon, hydrogen, oxygen, et cetera, et cetera. Yeah, I know some chemistry and a math talk, yeah? So that's the first thing. If I am given a group, I'm given a field, what are all the building blocks? And that changes. If I change, like I said, if I change the field K, if I change group G, that creates a whole new universe. Sometimes there are finitely many atoms. Finitely many, and atoms is not a technical term. I know in other areas of algebra it is, but just an analogy here. Are there finitely many irreducible representations? Are there infinitely many? And if I change the characteristic of my field, how does that change if I leave the group fixed? So that's what we want to know. We fix a group G and fix a group, fix a field K. What are the irreducible representations? All right. And the other question people like to ask, and this is what the latter half of my talk will discuss. If we're given a representation over a fixed field and a fixed group, what irreducible representations is it made up of? So, for example, if we have the representation, maybe it decomposes as V1 plus V2 plus V3, and V1, 2, and 3 are all irreducible representations. How can I decompose it? And so this is, again, using the analogy of atoms. Think molecules. So what atoms make up a given molecule? Well, you have a water molecule, 2 hydrogen atoms, 1 oxygen atom, and I know completely what water is made up of. All right, so I'll pause again. Is there any questions about what representation is, or some of these questions? Cool. Okay. Now, switching over to some geometry, smooth projective curves. So I'll just give the definition and talk about how algebra interacts with geometry here. So, what is a smooth projective curve? It is a collection of points in projective space, it's a projective curve, that is the common zero set of some collection of homogeneous polynomials. The fact that they're homogeneous is important. So, as a set, we can write a curve, a smooth curve as this. It's a collection of points in projective space, A naught through AN, in equivalence class. So that F, if I plug that point into various polynomials F, I get out 0, and this is for some F in some set of homogeneous polynomials. So the common zero set of some homogeneous polynomials. That's what a smooth projective curve is. And what makes it projective, as I said, is its points in projective space. What makes it smooth? Well, you take the Jacobian matrix of these homogeneous polynomials, and it has to have a particular rank. And that's what makes it smooth. And then what makes it a curve is that its function field, which I'll define here in a second, that its function field, which we'll denote by K parentheses big X, it's a field uniquely associated to the curve, is a finite extension of K adjoined T, the rational function field. So if you want, so curve is one-dimensional. So that's why it's a finite extension of K adjoined little t, some indeterminate little t. If it was a surface or something of dimension 2, 3, 4, the function field would be a finite extension of K adjoined finitely many transcendental elements. Right? So this is what makes it a curve. And so what is a function field? So it is, you can think of it as fractions of polynomials that are homogeneous of the same degree. So it's degree 2 over degree 2, and you need, I didn't put it all here, but and you need that the denominator, the little g here, is not 0 on any of the points in X. And really, it should be properly fractions of cosets. You have to mod out by the ideal generated by these homogeneous polynomials, but more or less, the elements of the function field are fractions of polynomials that are homogeneous of same degree. Okay. So that's what a projective curve is. What I want to emphasize here is that there's a curve, there's a function field, and you can go back and forth between them, and they're, with curves, unique. So given curves are isomorphic or homeomorphic, all the nice words that you want to say about them, if and only if their function fields are. I believe if you up the dimension and you don't look at curves but look at surfaces, that's not always true. I'm not sure about that. But here, that association is unique, and we're going to use that. So, What are we going to do with curves? Well, we're going to let G be a finite group, and we're going to let it act on the curve X. Just a regular old group action. And we get, then, through that, a morphism of curves, which I'm going to denote by a pi that goes from X to X mod G, where X mod G just denotes the orbits of X. And so I'm saying something here. I'm saying that this is a morphism of curves, which means that X mod G, the set of orbits, better be a curve. And it is. Believe me. So if you break up the set X into this set of disjoint set of orbits, every orbit can be uniquely identified with a point in the projective curve. And so we have this diagram, and we have that the field extension, so there is a field extension of the function field of X over the function field of this other curve, X mod G, which down here I call Y, is Galois with Galois group G. So in this middle diagram, we have X going down to Y, this morphism of curves, which Y is defined as X mod G. And then you have this extension of fields, which is Galois with Galois group G. And then here, what is the map? Pi. It sends X to, well, it's orbit. Okay. All right, and I just want to emphasize here that since I said that the function field of any curve is a finite extension of the rational function field, and so I just want to remind you that this field really is here. And certainly k adjoint little t is a finite extension of k adjoint little t. So what's the curve associated to it? Well, it turns out to be just the projective line. All right. So we've talked about representations, we've talked about projective curves, and this is the part where we put them together. Differentials. How do we put them together with differentials? Okay, so first we need to define a module of relative differential. So the idea is I want to take a K-algebra, I'm going to call it B here. So it's just a vector space where you know how to multiply things. And I want to define a differential map on B. That's the goal here. From D, the differential map that goes from B to this module that's defined here. And I want it to be linear, I want it to satisfy the product rule, the Leibniz rule, and I want it to be 0 on the elements of K. And so we force that to happen by defining it this way. Take the free module, free B module generated by the symbols dB, and then I quotient out by the necessary relations so that this map D is linear here, that it satisfies the product rule here, and that it's constant on elements of K. All right? So this is this B module. Let's look at some examples. So if I look at the polynomial ring in one variable, that's a K-algebra. What is its module of relative differentials? Well, it turns out to be the free module over the ring K bracket T generated by dt, so that you can think about it like this. If I take a polynomial in one variable, take its derivative, that's just f times dt, f prime times dt, and so that's intuitively why you get this, something to show there. And the example that we're going to come back to is the module of relative differentials for the function field of some curve x over k, that's a K-algebra. And it turns out that this has a similar form. It's just the function field dt, so an element, what does an element of this module look like? It looks like little f over little g dt, where f and g are homogeneous to the same degree. It doesn't always work out this nicely, but if I take the polynomial ring in n variables, then I get this direct sum of things that look like this k bracket t dt. Now I didn't put it up here, but if you look at the K-algebra that is polynomial ring in finitely many variables, and quotient out by some ideal, then it's this exact thing modulo some relations that depend on the ideal. Okay. So this is what the module of relative differential is for K-algebra. Any questions about this? Yes?
In your second bullet point, what is t on the right-hand side of the dt? Is t just an indeterminate? Or what is
Yes, it is, but specifically, it is the indeterminate, because remember, we said that a function field is a finite extension of K join those two, so it's that T. It's that T. Good question. Any other questions? All right. So, now, so that's a module. Now we're going to define a sheaf. So I'm just going to give you what the stalks of the sheaf are. Hopefully that'll be enough to give us the information about the sheaf. So what are they? So first of all, this is called the sheaf of relative differentials of x over k, given a smooth curve x. And we're going to denote it by omega x. And what are these stalks? They are modules of relative differentials for some rings BI. So that's what this stalk looks like. And in fact, with a curve, you only need 2 rings BI. So that every stalk will either look like the module of relative differentials for B1 or module of relative differentials for B2. But that's what these stalks are. They're these modules. Now, holomorphic differentials. The global sections of this sheaf are what are called holomorphic differentials. So we denote the global sections by this. Yes, you can define it using cohomology of sheaves, so that's where this notation comes from. But whenever you see this symbol on the screen, just think it's a vector space and it's associated to the curve x. All right, so again, this is just global section, so I'm just applying the sheaf omega x to x. That's what it means. And what is it as a set? So I didn't put the conditions here, but you can think of it, all the elements look like f dt in this function field dt with some conditions on f. So it's really a subset of the module of relative differentials for the function field of x over k. It lives inside there. So, what does that mean? Well, since the global sections live inside this module, we know that if we let a group act on x, then we get that its function field is a Galois extension. So that means that the group knows how to act on the field k adjoin big X. And so if the group acts on this field k of x, then certainly it knows how to act on k adjoin x dt, right? And so this is a vector space over k on which G knows how to act. So it's a representation. And what I want to know is, what is its, how does it decompose? What are the atoms that it's made up of? So, a representation theory of holomorphic differentials, as I just said. So, that was the general overview of defining things, but now specifically, what am I doing? Well, I'm looking at the Klein 4 group. So G from here on out will be Z2 cross Z2, the Klein 4 group, and K, so I'm going to write G as this direct product of sigma tau, and my K is going to be an algebraically closed field of characteristic 2. So this is my situation. So in this universe of this algebraically closed field of characteristic 2 and G being the Klein 4 group, what are the irreducible representations? And so this is my periodic table of elements, if you will. So whenever you see an n in the following table, it's some integer greater than or equal to 1. So here are the atoms in the left-hand corner, the left column. And if it's a representation, I need to tell you not only that it's a vector space, but how does G act? In this case, it's enough to tell you how sigma and tau act. So here we have the trivial representation, the one-dimensional vector space over K, where sigma and tau act by the 1-by-1 matrix 1. And then I won't go through all these, but then we have the 4-dimensional vector space, Kg, where sigma and tau act by these 4-by-4 matrices. And the only thing I want to point out in this last piece is, well, if n can be anything bigger than or equal to 1, this means that this part of the table is really an infinite piece. So in this universe, there are infinitely many atoms, infinitely many indecomposable representations that could possibly show up in a module, in a representation. So, what do we do with this? Well, the first thing that I've been looking at this semester is I'm in this situation of the guess that was exactly what I needed to write down. We have this general situation. We have this field extension of K of X over K of Y, this extension of fields with Galois group G. And again, for me, this is going to be Z mod 2 cross Z mod 2. And I want to compute the modular relative the holomorphic differentials for this curve and compute its structure. Well, this has already been looked at in a more general case in 1996. Calderon, Salvador, and Madan, they proved in general that if you have a cover, if you have a field extension like this of it's an elementary abelian extension, so anything that's p to the n, then they proved what the modular structure is in a more general sense. So for me, I just want p to be 2 and n to be 2 to get the climb forward. They proved what this modular structure is. However, their proof was very computational, very brute force. They just found an explicit basis for this representation, and then they just let the group act on it and saw what representations would show up. And it wasn't very pretty. But they did it, and they solved it for any extension of degree p to the n for any prime and any positive integer. So we looked at, my advisor, Dr. Blair, and myself, we looked at the specific case, and for now, we started off with this extension just being the rational function field, and saw if we could prove the structure of these holomorphic differentials in this case. So now this is just a morphism from X to P1, which is X mod G, and we got these 3 modules showing up, which of course coincides with what they proved here in 1996. And so with all these, we just go back one slide, you have infinitely many atoms here, and so it turns out that you only have 3 of them showing up. So here you have, the reason that the first subscript is 2n is because it's even dimensional of degree 2n, and same thing here. And then these last 2 are odd dimensional of degree, of dimension 2n plus 1. And so it turns out that the only 3 that show up are the trivial representation to some multiplicity L1, and this even dimensional irreducible representation of dimension 2 to some multiplicity, and a 3-dimensional, so 1, 2, and 3. That's all you have showing up in this specific case. And so a proof. So I want to give an outline of what were we thinking about, how is our method different than their method. So, as I said, their method was brute force. Here's the basis. Let's let the group act on it and see what happens. This method is very geometric. And so, since our module is defined in terms of this sheaf, let's see what we can say about the sheaf and how that affects the module. So, we filtered the sheaf into a sequence like this. So we have some subsheaves, omega x3, omega x2, omega x1. And then we looked at quotients of these quotient sheaves. So omega x3 mod omega x2. We said, what can we say about these things? What's the structure of this sheaf? Can we get a better description? And it turns out that these quotient sheaves are isomorphic to, in this case, I'll write it backwards here like this. Turns out that these quotient sheaves are isomorphic to the tensor product of a line bundle, OP1 dj, if you know what a line bundle is, tensored with omega P1. So this is the sheaf of relative differentials for the curve P1. And so what this did for us was it allowed us to use, so we used the Riemann-Roch theorem to then figure out, okay, what does that mean for the dimension of this quotient, these quotients? So again, H0x omega x, this is the vector space that we're trying to understand. And so we use this filtration of the sheaves to then get a filtration of the global sections of this sheaf and compute its dimensions using this isomorphism here. And so, in the final bullet, I just say we use dimension arguments to rule out possible indecomposable modules appearing. So the idea is we have this vector space, and I take quotients in it. So I take V mod V3, say this has dimension 5. V3 mod V2, this has dimension 3, whatever it may be. And so, okay, well, if that's the case, then there's only certain indecomposable modules that could show up. So that was the idea, and it's geometric because we're using sheaves. And of course, I like it, but I really like the method because we don't have to just attack it by brute force as they did. So I just finished up. I'm really excited about it. I just been working on this proof for this whole semester, and I actually just finished it up last weekend. I brought it into my advisor. If you know my advisor, she can be very intimidating, but very kind at the same time. She scrutinized every line, gave me some pushback, but she said, "Oh, this is great." I think so. So it works. Yeah. So this is the result of my first semester of research. So that's all I have. I'll of course take questions. Thank you all for listening.